All right, so more often, the solids that we get and the solids that are become interesting when in finding volumes are not solids that have uniform cross section, because those are kind of basic solids. I mean, you saw in the previous example we did a pyramid. Now, you can get some interesting solids that way, but another more common way of creating solids is to take a curve like you see here in this picture. And this particular curve, we've got a limit. We're running this curve from 0 to 2. And what you need to do is imagine the region, right? This region that is bounded by the curve and the x-axis and the limits of integration. And what you want to do is you want to imagine rotating this around the x-axis. All right? So you have to have kind of a, you know, a good ability to visualize this. So if we take our curve, I'll reproduce it here so we can have both the original region as well as this is called a solid of revolution. So what you want to do is you want to imagine taking this solid and let's rotate it. We can rotate it around any line that we want, any horizontal or vertical line. We're going to rotate it around the x-axis. And so if you rotate it or revolve it around the x-axis, what happens is you get a shape that is like this. This part rotates and kind of makes this little circular, right? So we're just rotating it. It's like we're spinning it on the x-axis. This side will rotate. Let's see, this is the curve y equals, you should mention that. This is the curve y equals x squared plus 1. So that is up there at 5. Right here is 5. So it's going to rotate down here to a negative 5. We got our curve itself that rotates down. And so when you rotate this, revolve it around the x-axis, you get this shape here. It's kind of like a trumpet, the end of a trumpet, but it is all filled in. Okay, that's the thing. That's why you imagine that shaded region rotating and the solid that it produces. And so it's called a solid revolution. And so what we want to do is we want to find the volume of this weird little trumpet bell kind of thing. And so we're going to take a real similar approach to the approach we took in the previous example. We're going to go over here a distance somewhere between our limits of integration, somewhere between 0 and 2. We'll call it x. So maybe somewhere right in here. And we're going to slice this thing. Okay? And when you slice it, again, we're going to slice it so that the thickness, which we call dx, is so thin that we don't have to worry about the fact that this little section is actually a curve. We're going to just imagine, since we sliced it so thin, we're just going to imagine that is straight across. And when you visualize the shape you get from that slice, you're going to get a disc. Right? A solid disc. Okay? And so we want to find the volume of that one little disc, and then we'll integrate that volume, integrate the dV, and it will give us the volume of the entire shape. Because notice, if I were to slice over here, right? If I were to slice over here, I would get a bigger disc, right? I'd get a bigger disc. So I'm getting kind of similar volume, similar shaped objects here, but the way I get this object is by a revolution. So what I need to do is I need to figure out what the dimensions of this disc are so that I can find its volume. Let me input this. Remember, this was x where we made the slice. So in order to find the volume of a shape like this, this is basically, if you want to think of it, it's a really skinny or a really short can, a cylinder, right? So this is a cylinder. The reason I bring that up is because we have a nice, neat formula for the volume of a cylinder. It's pi r squared h, right? So what we need is we need this dimension, the radius, okay? And then we need its h. Now its h is right here. There's its h. There's its thickness, right? Because our cylinders look like this, with a radius of r and a height of h. So our h is there. But the nice thing about the h is it's just dx. Okay, so we have the h. All we need is the radius. All right? And so the radius, if we go back to our slicing picture, we went over a distance x. The radius of this particular disk is that distance right there, the distance up to the function. So if I plug in x into the function, that's going to give me the radius. So that is to say, this radius right here is x squared plus 1. I just plugged in x into the function y equals x squared. And now I can write the volume of this little slice. dv, remember we call it. It's pi times the radius squared times the height, which is dx. And that is the volume of that cylinder, or that disk. And so if I want to find the entire volume of the entire solid, I integrate or add up all of those little volumes. So it's going to look like this. We'll put in a pi x squared plus 1 squared dx. We started slicing at 0. We stopped slicing at 2. And so that is going to be the integral we need to evaluate in order to find this volume. So just quickly doing a couple things, right? So I'd pull the pi out. I would square all this. And this is an easy one to evaluate because the pi is going to hang out there. And we're going to have x to the 5 over 5 plus 2. Let's write it this way. 2x to the 3 over 3 plus x evaluated from 0 to 2. And so we get pi. Plug in a 2, we're going to get 32 fifths plus 16 thirds plus 2 minus pi times 0. And so I went ahead and finished that up. Ended up with 43.14 cubic inches as our volume. And so we can really create some interesting shapes by taking a curve in a region, rotating it around the x or the y axis, and then finding the volume of that solid revolution. So I'll post a couple more examples here for you to observe, but this gets you started on the process.